This conference will now be recorded.
Wonderful. Okay, so welcome everyone. It's a pleasure to introduce one of my friends, Alex. Alex Forensic received his bachelor and master and PhD, all in electrical engineering and computer engineering department from UCSD, University of California, San Diego, in 2012, 2015, and 2020. So he currently is a postdoc researcher at UCSD, and during his PhD studies, he interned in IBM T.J. Watson Research Center in Yorktown Heights, New York. His research interests include data center networking, optical switching, and reconfigurable hardware. So today, Alex is going to talk about Corundum, which is basically an open source NIC that you can implement it basically on various boards on FPGA. So without further ado, Alex, the floor is yours.
All right. Well, I guess I can pull up my slides. I'm not sure. It says become the presenter to start sharing your screen. Do I need to push a button for that, or?
You should be the presenter now.
Ah, okay. There we go. Let me get this thing going here. Hold on a second. Let me get this thing organized. Okay. I think that'll work. All right. I will share that. Okay. There we go. All right. So my name is Alex Forensic. Like Ahmad said, I am a postdoctoral researcher at UC San Diego. And today I'm going to talk about Corundum, which is this open source 100 gigabit per second FPGA-based NIC that I've been working on for the past couple of years. Before I talk too much about Corundum, what I want to do is give a little bit of background about the research that we've been doing at UCSD, because that kind of sets the stage a little bit for the development of Corundum. And it explains some of the architectural features and whatnot that we've been developing it to implement. All right, so first a little bit of background on the research, right? So data centers are traditionally built using packet switches, right? So packet switches are great. They're distributed. They operate on a packet by packet basis. However, packet switch bandwidth and link bandwidth is not increasing fast enough to keep up with the demands of modern data center applications. So at UCSD, we've been looking at some alternative switching technologies that might be able to improve the situation somewhat. And one of these is circuit switching. So the idea with circuit switching is we're going to operate at the level of links instead of the level of packets. So instead of looking at every single packet and making a routing decision, we're just going to make and break connections. And if you can do this in the optical domain, then you can support very high data rates per port, and you have a significant potential for power and cost savings because you don't have all these expensive power-hungry switch chips, and you don't have you're not consuming nearly as much power in the actual optical switches. You don't have as many transceivers. There's a number of advantages, but it's a completely different paradigm, right? Because we're working on the level of links. And in order to take advantage of these switches, you need different network architectures, you need time synchronization, you need transmission control, you need fast locking receivers, new protocols, you need a whole bunch of different technologies, and all these need to work together in order for the complete system to work. At UCSD, we don't just work at this at a theoretical level. We actually build research hardware, so we can actually experiment with some of the trade-offs and some of the different technologies to get a sense of how all the pieces are going to fit together and how this is going to work as a complete system. All right, so let's see. In order to run this at a reasonable scale, what we want to be able to do is to use commercial hardware as much as possible to build this stuff. But the problem is commercial hardware is not really designed for this type of application. It's all designed with packet switching in mind. And one of the most important features that we need is kind of microsecond precision transmission control. We've tried to do this in software for years, but it hasn't really worked. And we've run into a bunch of roadblocks. We need some sort of hardware to make that work. And this is where Corundum comes in. We decided we need this feature. Without this feature, we can't really experiment fully with these experimental switches that we're building. So let's make a NIC. All right, so moving on to Corundum. The network interface controller, or NIC, is a hardware component that connects the software world to the network. As line rates have been increasing, NIC functionality has been evolving. To deal with these high line rates, we need to push more and more load off of the CPU. So there's protocol and segmentation offloading that NICs can carry out to support higher line rate operations. There's also extensions for virtualization, various packet processing things, SRIOV, things like that, where the NIC takes, more of an active role. So for virtualization, it might even act kind of like a switch as well as a NIC. And then NICs can also implement various packet processing techniques. I know it's RMT pipelines are becoming more common as something to build into, a smart NIC. Network architectures, applications, and protocols all benefit from NIC hardware features. If you want to build new network architectures, new applications, and new protocols, it makes sense to have a NIC that can implement, new hardware features. One feature, at least specifically one that we're interested in at UCSD, is precise control of packet transmission. So this has a bunch of different applications. Obviously, we're interested in the TDMA and circuit switching for UCSD, but this is also useful for rate limiting, for flow control, for congestion control, and probably lots of other applications that we haven't thought of yet. However, sub-microsecond control is not feasible in software. It's just, if you don't have a real-time operating system, if the NICs are not designed to provide any support for that necessarily, it's just not going to work. And we found this out the hard way by trying a bunch of different techniques and, basically not coming up with anything particularly promising in terms of performance. There's very little hardware support for this type of stuff in commercial NICs. Generally, they have a very limited number of queues, which means you can't really divide up traffic in a very fine-grained way. And they have very limited control over transmit scheduling. Maybe you got some rate limiters, but that's generally about it. They might have like RMT pipelines and things like that with smart NICs, but in general, these have architectural limitations in terms of doing precise timing. They're designed for packet comes in, you make a modification, you send it on its way as quickly as possible. You don't hold on to it. But that's what we're trying to do, is to hold on to packets for a while and then release them in a very controlled fashion. We know this kind of stuff is possible to do on an FPGA. I mean, I'm not going to say it's trivial, but it's pretty easy to make an FPGA transmit packets on a very fine-grained time scale, on a very precise pacing. But we want to build a NIC. We don't want to send, synthetic traffic from an FPGA. So we want to start with some sort of, an FPGA-based reference design that's a NIC that we can build this functionality on top of. When we started working on this project a couple of years ago, there really wasn't anything available that we could use. There was, you could get like a DMA core from Xilinx or something like that, and there were a few companies that had their totally proprietary FPGA-based solutions, but we weren't going to be able to modify their code necessarily to do what we wanted. Because again, we weren't trying to do just packet processing, we were trying to make a more low-level change to the NIC functionality. So this is where Corundum comes in. I spent the last, basically 2.5 years now probably, working on this open source NIC design. And the idea is to provide a high performance reference NIC that has similar performance to a commercially available NIC. Maybe it doesn't have all the features, but can move data. But it's completely open source. So you can go in at any level and make whatever change you want to support the features that you need. And the key application is to support the hardware prototyping of experimental networks and protocols. I mean, it's unlikely somebody's going to want to spend the thousands of dollars per host to put an FPGA in there, but in a research context, it makes a lot of sense. And then the features that you prototype on here could then end up in the next generation of commercial ASIC-based NICs. All right, so let's get into the details a little bit. So Corundum, as I said, it's a high-performance, open-source FPGA-based NIC. It supports PCIe Gen 3 by 16, or I mean, really whatever the FPGA that we're running on supports. It can connect with multiple 10G, 25G, or 100G Ethernet ports. It has a fully custom high-performance DMA engine to interface with the host and a Linux driver to connect with the Linux kernel networking stack. It can control the data transmission on a per destination basis using tens of thousands of hardware queues, and it has customizable per port schedulers. So you can have multiple ports. Each port can be, running its own schedule, running its own fair queuing or whatever. Using these capabilities, we can perform microsecond precision TDMA. So as part of that, we need to implement IEEE 1588 PTP timestamping. So we have a hardware clock on the NIC and timestamping support in the Macs. And then the timestamps are all returned to the host as in the completion data with all the packets. And this is, we get pretty high performance with this system. The data rate that we reported in the FCCM paper is over 60 gigabits per second for 1.5 kMTU frames. We're hoping to improve that with some improvements and modifications to the driver and also to the gateware. So this is all open source. I got a link to GitHub here. I'll have that again at the end of the presentation for you guys to take a look. Okay, so this is a block diagram of everything that we have inside of the NIC. At the top level, just sitting right on the FPGA, we have a lot of interfacing components. So this has, the PCI Express hard IP that actually is responsible for bringing up the, the physical layer PCI Express link to the host. We have an AXI Lite register interface that's used to interface with, many components inside the design. We've got the DMA interface module that's responsible for carrying out all of the data transfers with the host, and we have a PTP hardware clock that can be synchronized with the host and synchronized over the network. On the other side of this, we have the Ethernet interface components, the MACs and the PHYs, and this is where the PTP timestamping is implemented. Inside of the top level, we have one or more interface modules. So each interface module will be exposed to the operating system as a separate network interface. So you can have one interface module on the card and it will show up as a single interface. You can put two on there and it'll show up as having two network ports. The interface module contains all of the transmit and receive queues, and it also contains some of the descriptor management logic. Inside of the interface, we can then have one or more port modules. So the port module contains kind of the main data path. This is responsible for coordinating all of the DMA operations for sending and receiving packets. So what this does is, so this has the transmit and receive engines. It has the internal DMA components that connect to the Macs. So every Mac is going to have one port module. This one also contains the transmit scheduler that decides which packets are going to be sent and at what time. And the scheduler modules can be connected to PTP time. They can be fed information about other events that are taking place in the network. This also has some of the basic offloads, the checksum and hash offload components. So let's talk a little bit about some of the components that are inside of Corundum in a little bit more detail. So one of the most important pieces is the transmit scheduler. And this is kind of the whole reason of building Corundum is we wanted something that we could, experiment with the transmit scheduler and implement some sort of a TDMA scheduler on top of. The transmit scheduler determines what queues to transmit from at any given time. The default scheduler in Corundum is round robin, but it's a single module. You can take it out and replace it with something more complicated if you want to do that. So if you wanted to implement weighted fair queuing, or there's a bunch of papers that came out over the past few years, Scenic, Carousel, Pio, Loom, it would be possible to take one of those schedulers and drop that inside Corundum and run it. The transmit scheduler, as I mentioned before, it can be connected to various other hardware interfaces, including the PTP clock or other event sources, and using that you can implement TDMA, or you can implement things like hardware congestion control, HPCC, NDP, etc. Coupled with the transmit scheduler, we also have all of the queues that connect the host to the NIC. Now each queue is an independent channel between hardware and software, right? Hardware controls one end, software controls the other end. So you can enqueue packets from software, and then the NIC can dequeue them and send them. Traditional NICs support something on the order of maybe 100 queues or so for load balancing. And the idea for most NICs is you're going to provide one queue to each CPU core or one queue to each virtual machine, and then the NIC is just going to, round robin across the data in those queues. And there's not really any relationship between the data that gets enqueued in a particular queue. If we're going to do TDMA, like on a per destination basis, in order to do that, we need a very large number of queues, right? We want one queue per destination or something along those lines. So in Corundum, we've taken great care to make the queue state very small and to store it efficiently in block RAM on the FPGA. And as a result, we can store the state for tens of thousands of independent queues. So it takes 128 bits per queue for that state, and on the UltraScale Plus FPGAs that have UltraRAM blocks, we can fit 8192 queues into 4 UltraRAM blocks. I think that's the default. If you go download the designs on GitHub right now, anything that targets UltraScale Plus by default has 8192 transmit queues. So that I'm not sure how that compares to every existing commercial NIC, but I know that's a lot more than what most NICs can provide. In terms of architectural features of Corundum, one thing that's kind of interesting is that it supports multiple ports per interface. I'm not aware of any other NIC that does something like this. It's possible with smart NICs you can reroute packets from one port to another. But the basic idea here is to permit striping and migrating of flows from one port to another under control of the hardware schedulers. So with most traditional NICs, if you want to decide what port you're going to send the packet out of, you have to make that decision when you're handing the packet off to the driver or somewhere inside the network stack in software. And then it goes into the queue, makes its way through the queue, and then the NIC will send it on the wire. With Corundum, we make that decision on the other end of the queue. So when we're actually dequeuing the packets in order to send them, that's when we can decide which port we're going to send it out of. And in this way, we'll present a single interface to the operating system that corresponds to however many ports are associated with that interface in hardware. And this can be useful from an architectural standpoint if you're building some sort of a parallel network that has P-factory type thing where you have multiple uplinks to different networks. And you can use this to control which flows are going where. Now, NIC has a host interface. Corundum uses PCI Express to connect from the FPGA to the host, and we use a custom DMA engine to carry out all the transfers. And the reason we went for a custom one is because for a few reasons. One of them is that most of the existing cores, XDMA and I don't think QDMA was available when we started working on this, or at least we weren't aware of it. RIFA is another one. They're all designed for compute offload applications where the FPGA basically has no control over what the DMA engine is doing, but the software running on the host will say, read this block of data or write this data to this location. For a NIC, you really need the FPGA to be more in the driver's seat of what is going on over a PCI Express interface. So the cores that were available didn't really have the capabilities that we needed, and then also the simulation framework that we were using didn't support simulating some of these commercial IP cores. So we decided, okay, we're going to write our own DMA engine. And also the DMA engine is really integral to the performance of the NIC. So if we run into a problem that ties back to the performance of the DMA engine, if we didn't have a custom one in the first place, we kind of would have been hosed. And then we also put together a rather extensive simulation framework in Python for simulating the entire system, including the custom DMA engine and all of the components on the NIC. And this is super important because debugging in hardware is a real pain. So if we can simulate the entire system in software, including the integration between the DMA engine and the other components, then we can work out a lot of bugs beforehand, or before we load it onto the FPGA where we have minimal visibility. So I'm going to talk a little bit about this DMA engine because as it's evolved, I think it's become rather interesting. So the way the DMA subsystem in Corundum is built is it's split up into a couple of pieces. So one of them is the DMA interface module. So this one, on one side, it will interface with the hard IP core on the FPGA for PCI Express or whatever. But actually, it doesn't have to be PCI Express. You could actually have an AXI interface to, for example, an SoC type FPGA where you have the ARM cores as the host. And then on the other side of that, we have this segmented memory interface that connects through simple dual port RAMs that sit inside the FPGA. And then inside we have client modules which can interface with these simple dual port RAMs, and then they provide various internal interfaces. We can have AXI stream, you can have AXI master, AXI slave. You could also make Avalon ones if you want Avalon streaming, Avalon memory mapped, whatever you want, you can mix and match it. The internal interfaces can be different widths, they can be different protocols, and because we have these internal RAMs, they can even be running in different clock domains. So if you want one of these to feed, some high-speed processing pipeline, you can get clock domain crossing for free with this architecture. Let's see here, and the segment interface that we use internally is sort of based on AXI Lite. It's double the width of the PCI Express interface. So if the PCI Express has like a 512-bit streaming interface, we'll have a 1024-bit wide segmented interface. And this means you can do same cycle access to adjacent memory locations, which is extremely powerful because now we can actually run that PCI Express link at 100% utilization. In the previous iteration of this, we used AXI, and we could not run the PCI Express link anywhere near 100% utilization because of limitations of what we could do over AXI. We also use a separate select signal instead of address decoding, and the interconnect preserves the ordering, so we don't need to have ID signals and whatnot. Also, we have parameterizable interconnect components, so you can very easily change, how many ports you have based on a Verilog parameter, and the interconnect components will, figure out what to do with all the select signals, and they'll manage the request and completion routing and the traffic over the segmented interface. And this one I think could be super useful for FPGA acceleration shells. So if you look at, say, what Xilinx provides with their Alveo cards, they have a couple different shells. They have one for networking applications that has streaming interfaces, and they have kind of their normal shell, which has a memory mapped interface. Well, if you exposed like this generic segmented interface, then you can adapt that to whatever you need inside of the user logic. And you can make the region a little bit bigger for the user logic, and then you can get this clock domain crossing capability, and you can mix and match, whatever internal interfaces you want, and you only need, one shell. Makes it more generic. So we haven't done anything with that really because we're not looking at partial reconfiguration at this point in time, but this could be a very interesting capability for somebody to look at. The other component that I mentioned briefly is that we have a simulation framework. Originally it was written in MyHDL, and then I ported it to CocoaTV. This has a model of the entire PCI Express system, right? So the root complex, switches, endpoints, etc. It supports configuration spaces, memory mapped I/O, DMA, peer-to-peer DMA, message signal interrupts, and it does the enumeration and memory management that's necessary for bringing up the entire interface. It also has models, very basic functional models of the PCI Express IP cores that are on the FPGAs that we're using. And these IP cores are what bridge the PCI Express infrastructure model to the Verilog design. And these are basically a functional simulation of the hard IP core interfaces. So using these, we can run the Verilog design with this model and see how the whole system is going to work together. However, the models right now are somewhat incomplete. They're good enough for functional testing, but they're not timing accurate. And they're also only at the transaction layer right now. So the link layer, flow control, LTSSM and whatnot are not yet implemented. Eventually, we hope to have things implemented to the point where we can support the pipe interface. And then we'll be able to connect it using a commercial simulator to the PCI Express IP core. We can do a kind of top level simulation of the whole thing. We're not at that point yet, but eventually that would be very useful to do because then we can root out even more possible issues in terms of interfacing through the vendor IP cores. All right, so once we got the whole thing working, we went ahead and loaded it onto an Alpha Data FPGA board and stuck that in a pretty powerful Dell server with Xeon Gold 6138 CPUs. We basically set up two connections in parallel. We had the 100G Corundum NIC connected to a Mellanox ConnectX-5 NIC, and then we had a pair of ConnectX-5 NICs cross-connected. And we loaded both of those links with multiple instances of iPerf3. We tested 1500 byte and 9 KB MTU frames, and we compared the performance against a pair of Mellanox ConnectX-5 NICs. So this is what that looks like with 9 KB MTU. We can get quite close to the 100G line rate when running the transmit and receive processes separately. When you run them at the same time, then we suffer a little bit on RX. I'm thinking that this is probably a driver issue and that we may be able to resolve that with some optimizations. We'll see about that. And then for 1.5 KB MTUs, our performance suffers a little bit more, partially because of some driver memory management things, and also partially because we're probably not reading descriptors in the most efficient way right now, but we're going to be addressing that soon. So these are kind of preliminary figures as what we published in FCCM, but once we make a few more changes to Corundum, hopefully we'll be able to improve the performance quite a bit. All right, so now that we have Corundum, what do we use it for? Well, one thing you can do is use it as a data path for novel transmit schedulers. I mean, let's say you have a new scheduler idea. You can take it and you can use Corundum as a data path. You can drop your scheduler into it and run it, and set this up across a number of machines and, see how it works kind of at scale. You can also instrument Corundum for performance measurements, right? All the network traffic is passing through Corundum. You can look at what's going on the DMA side. You can look at what's going on, in the data path to see, what's happening. And you can do basically zero overhead measurements of network performance. You can also, since it's running on an FPGA, on a lot of boards that don't have like a PHY chip, we have direct access to the physical layer connections to the optical transceiver. So that means we can do physical layer measurements, BER measurements, things like that. And we can also develop new wire protocols, right? That's something that we're going to be looking at actually for some of the circuit switching applications. Also, Corundum can be used in isolation as a NIC, or you can just take the DMA part of it and use that as a packet DMA engine for, some other type of system. You want to do packet radio or something, you can use that as a DMA engine for that. So I'm going to be talking about two main applications over the next couple of slides. One of them is the TDMA for microsecond circuit switching, and the other one is the PHY layer BER measurement for link characterization. All right, so like I said before, Corundum has been designed for optical networking, and as a result, we have a bunch of features that kind of fit together to support optical networking applications. So obviously, we need this high precision time synchronization in order to provide high precision TDMA. And we also need this high number of transmit queues for per destination control. And by having this PHY layer access, we can use that for physical layer link characterization, and we can also develop custom line protocols. And then we also have additional reconfigurable hardware available for implementing custom routing protocols to support these circuit switching applications. So here's one of the switches that we've been working on at UCSD. This is called the rotor switch. And what we do for this is we take a hard disk platter, basically, and we pattern these diffraction gratings around it using a laser writing process. And then this is assembled along with 5 fiber arrays. And we can take light from the center fiber array and couple it into one of the 4 outer fiber arrays. And the great thing about this setup is that it has very good optical properties, very low crosstalk, relatively low insertion loss, low enough to the point where you don't need any optical amplification in order to use this in the system. And we also have a very wide spectral range that you can fit through the fibers. So this means you can put, a huge amount of data, DWDM or WDM or whatever you want, across each one of the connections through this thing. So the way it works is in the center fiber array, we have all the transmitters and receivers and all the hosts connected. And then in the other 4 fiber arrays, we loop those back to form 4 network topologies that we cycle through with this switch. And then we have a motor controller, which locks the rotation of the disk to PTP time. So we synchronize all the hosts to PTP time, we synchronize the disk to PTP time, and then we can send data through the switch. So we have this thing all racked up in the machine room in the ECE department at UCSD. And we have 9 servers hooked up to it that are loaded up with the FPGA-based NICs running Corundum. And using this, so we've actually run into some fabrication issues with the switch. It doesn't work quite right at this point, but we can use the PHY layer access capabilities of Corundum to precisely characterize what the switch performance looks like. And in this case, what we're doing is we're measuring the BER, right, the error rate, and we can relate this to basically the position on the disk. So what this heat map is showing is one complete revolution of the disk, and this shows where we are seeing bit errors on the disk. Now we would expect to see one band as it switches from one grading to the next, and we see that, but we also see some other spots around here that indicate some point defects that we need to go look at in the manufacturing process. We're looking at getting another disk made now that corrects some of these, so hopefully in a few months we'll have a much better looking heat map and we'll actually be able to use all the paths. But if you look at this closely, it turns out that there's actually some paths that don't have these point defects in here. So it turns out that we can take this and connect it up with the TDMA scheduler, and we can actually run an application. So the application we ran is iPerf, not particularly interesting, but this is the first time we've been able to run, a real data center application that's just running, standard TCP connections, not we're not just sending a bunch of random packets with a packet generator, but we have a TCP connection going through this, and it worked. So that's pretty cool. So the other thing that we're going to be looking at some point is potentially working on some new line protocols that are more geared towards circuit switching applications. So at 10 gig and 100 gig, or sorry, at 10 gig and 25 gig, it's not too bad because you just have one connection. You mainly just have to worry about CDR lock time and frame sync. Frame sync is about 10 microseconds or so. So if we're switching, in 10 microseconds, that works out nicely. But if you're using, say, a 100 gig link, well, now you have to bond the lanes together, and for that you have to wait for alignment marker lock, which takes like 200 microseconds, which is longer than the cycle time that we want for the switch. And then if you're using FEC, well, now you have to wait milliseconds to get the FEC block lock. So we might need to make some modifications to some of these protocols to speed some of these things up. There's no reason that alignment has to take 200 microseconds. It's just it's implemented in a very low overhead way. But if we make some changes to it to make the physical layer, say, aware of the switching of the optical switch, then it would be possible to improve most of these times significantly. And Corundum provides a platform for doing this kind of thing. You can't do this on a commercial NIC because they always bake this into the silicon. But with Corundum, we can actually take a look at that, and then we can run it with real data center applications at a reasonable scale. But we're not the only ones using Corundum. It's been publicly available for like a year and a half now or so. There's a couple of papers that have actually used Corundum. These are not papers that have simply cited it, but they're actually doing something interesting with it. So this one is something called Symbricks. And the idea with this paper is to be able to trade simulation speed versus accuracy and repeatability. And they use Corundum kind of as a reference NIC. So with this framework, you can select between running a virtual machine or running a cycle accurate CPU simulator, and then underneath that you can run several different NICs. They have a functional model of Intel X710. They have a functional model of Corundum, and then you can also run the Corundum RTL inside of Verilator underneath this simulator. And then you can connect it to NS3, or you can connect it to the network via TAP or whatever. So this looks like it could be a really cool framework for working with various networking applications. And then I also saw earlier this year this other paper came out called Menshen, and they built an RMT pipeline, but they used Corundum kind of as a host interface. So Corundum plus Menshen kind of forms a smart NIC type thing with that's capable of doing the RMT pipeline packet processing and then connecting to the host with Corundum. So this is one of the applications I was mentioning before. You can take Corundum and use it as a host interface, or you can take Corundum and you can drop packet processing components between the Corundum core DMA components and the wire. All right, so I'll talk a little bit about the ecosystem. The idea with Corundum is to provide a kind of a complete prototyping platform. So we have a high performance core data path and drivers that's extensible both in hardware and in software. We want to be able to provide wide device support. Currently, we run on Xilinx Virtex 7 through UltraScale Plus. We're going to be adding support for SoC devices, so like the Zynq MP-SoC. So this is where the ARM cores will act as the host instead of a host server connected over PCI Express. And we also want to add support for Intel devices, so Arria 10, Stratix 10, Stratix 10 DX and MX, maybe Agilex. We'll see. We also want to provide extensive software support. So right now we have a driver for the Linux kernel networking stack. Hopefully at some point we'll extend that to DPDK. We've also been working a little bit with Xilinx Research Labs over possibly fitting this into OpenNIC/NetFPGA 2020 somehow. So let's see. In the near future, we're looking to improve the driver performance to get the to improve the line rates that we're achieving. We're also going to look at supporting DPDK, MPI, libfabric, possibly other networking APIs. And we're also looking at making a bunch of improvements to the gateware. So variable length descriptors is one big thing that I'm going to be working on soon. That will hopefully improve some of the performance in terms of reading descriptors over the bus, and especially for smaller packet sizes. And it'll also provide the capability of passing per packet metadata to components on the FPGA that do packet processing. We're also looking at implementing LSO, SRIOV, and some other stuff, but we'll see. Some of these are more long-term type things. We're also going to be looking at putting together some extensions to facilitate experimental protocols and whatnot. This is more of a kind of a control path for some applications you might want to put on the FPGA, you know, how you can interface with that from a user space application or from the driver. The end goal is kind of to provide a an open full stack networking ecosystem, right? So if you take Corundum, you have a DPDK driver, you have a user space networking stack, then it's fully open source from the application layer all the way down to the wire. You can pull any piece of that out and, you know, tinker with whatever you want to implement, you know, whatever crazy idea you might have in terms of customized protocols or, you know, supporting your application to do some very low level interfacing over the wire. So we're also looking for contributors. I'm the only one that's been working on this for the last couple of years. It would be great to have some more people. If you're interested in working on Corundum, if you know about DPDK or Linux kernel internals, you know, you can help improve the Corundum driver or the gateware. Also, if you have an application in mind for Corundum, you know, let's bounce some ideas around. I know a lot more about how the Corundum internal architecture works. We can probably figure out how best to map your application onto that. So we got a GitHub repository, we got a mailing list. So you're more than welcome to take a look at the repository and go join the mailing list. If you have any questions, you can post on there. I send around announcements occasionally. That's about it. Thanks for your time. I'll take any questions now.
Thank you, Alex. So let's open the floor for questions.
So I have few questions for Alex.
Sure.
Yeah. So first of all, I was reading a paper some time ago about a system called Panic,
right,
which is using Corundum. And my understanding, please correct me if I am wrong, that they are using the physical layer aspects of your system, may not be using the software, but my understanding might be wrong. The other thing is they support multi-tenant, and I want to know how you support the multi-tenant networks in your NIC.
With Panic, I'm gonna have to go take another look at that paper, but I seem to remember that they said basically we can use Corundum as a host, but I don't think they actually used it for most of their characterization. I think they ended up putting together some sort of a packet generator for testing that.
In their paper, they said they use it amongst other things.
I'll have to take a look at that paper and refresh my memory on that, because my understanding was that they ended up not using it for their evaluation because the performance wasn't up to what they were hoping for. But yeah, for multi-tenant stuff, what?
Your information might be more up to date. I don't know.
Right. I mean, last I remembered, I was actually taking a look at what code that they had published, and they didn't have any Corundum code in what they had published. As in, what they published, you could run it without pulling in Corundum at all. So, but I could be getting some wires crossed. I will take a look at that and get back to you if you want in terms of what Panic is doing.
In Corundum, how you support the multi-tenant?
Well, right now we don't have any hardware support for multi-tenant,
Exactly.
and there's a couple reasons for that. The main one is that we don't have any support for any kind of flow steering right now. So that means that we can't put packets into queues, you know, based on the destination MAC address. That's a feature that we want to implement at some point, and that's going to be probably one of the most important features for any kind of multi-tenant sort of application. For what we're doing in the lab right now, we don't care about multi-tenant. But in terms of a feature of Corundum, I think there's a lot of people that could take advantage of that. And that's definitely a feature that I would like to implement if there's some people that would like to help make that happen.
My second question is related to programmability. Since you work with Xilinx, do you support P4?
Well, so you can put whatever you want in the packet processing pipeline between the the main kind of core data path logic and the transceivers. Right now, we don't really do any kind of packet processing on the NIC. We're not intending to be a smart NIC at this point. We're just intending to be just a kind of a dumb NIC. And the idea is that you can go in and you can modify the kind of the DMA side, and you can control the movement and the flow of data. But you can very easily add whatever packet processing you want between the core data path that's doing all the DMA and the interfaces. So if you want to do P4, you can use the Xilinx tools to create your P4 packet processing block and then drop that on the NIC.
In one of your slides, you provided performance for 1.5 kbytes Ethernet frame. Have you tried it the maximum, which is 2K? The maximum size for Ethernet frame is 2K. Have you looked at 2K? Have you tested the system with 2K
2K?
bytes?
Well, the max size is for jumbo frames is 9K. So those are kind of the standards that people are using. It's either 9K or 1.5K, or people care about really small frames. And let's just say the packet rate of Corundum could use some work. So we haven't really done too much testing with small frames. And the other thing is that I don't think any 100 gig NIC can achieve line rate performance with minimum length frames. So minimum length is 60 byte packets.
64.
The FCS counts as 4. So if you remove the FCS, then it's 60 bytes.
Okay.
I've made that mistake before. In fact, I have a block in Corundum that pads out the frames to the minimum length. And the first time I wrote that, I thought, oh, I got to pad it out to 64. Well, yeah, that was wrong. I had to pad it out to 60 because the Mac inserts the FCS, and that makes it 64. So
Got it.
But yeah, I have not done any testing kind of at that level, because even just moving that data over PCI Express is a problem. There's too much PCI Express bandwidth. If you're reading each packet in a separate DMA operation, it's impossible to get 100 gigabits per second over a Gen 3x16 link.
My last question is load balancing. If you present an interface or an abstraction to the applications where a flow packets can egress multiple different queues for load balancing, and how you will maintain packet ordering for a given flow?
Well, so within a queue, you maintain ordering, by default. If the application is sending data across multiple queues, well, then it's up to the application to be able to deal with reordering. This is something that if you're building a parallel network and you're going to be sending a flow across, multiple parallel paths at the same time, you can't do that. You can't maintain ordering in the NIC. You're going to get reordering, and then you're going to have to get stuff back in order somehow at the receive end. And we're not doing anything like that in Corundum right now. Maybe that's something we could look into doing in the future if there's a compelling application for it.
Since you know that in Ethernet in IEEE 802.1, they have this standard called link aggregation, where the application, where multiple links look like one logical link to the applications. So the application doesn't, you just send the traffic or packets, and link aggregation protocol and mechanisms can load balance this. You know this. So application is not even aware that there are multiple links, and there is an associated protocol with link aggregation, where if you would like for load balancing or performance reasons to send some packets on one link and the other packets on another link in the same aggregation, then you have to make sure that all the packets on the first link are sent first before you send the packets on the second link to maintain packet ordering. So that's really part of the link aggregation protocol.
Right. So I think the way most of the link aggregation stuff works is that basically the transmit packets will be hashed, and then you'll use the hash to determine, you'll use the flow hash to determine which link to use.
Exactly.
Possibly with some additional stuff there. So basically each connection should only be going down one of the links. The thing with Corundum, though, is that we do support multiple ports, but this is more in the sense that these ports are not necessarily going to be going to the same place, right? If instead of doing, I mean, we could do something like that in Corundum and do, some sort of hashing and whatnot. But the idea here is that you might actually have multiple parallel networks, and you'll have one link to each of these parallel networks. With link aggregation, all those links are going, they all form a point-to-point link. You got, usually between two switches, right? You might have two switches and you got 4 connections on one switch that are hooked up to 4 ports on the other switch, and you can make that into a single lag. So that makes a lot of sense for that type of thing. But for what we're looking at is, okay, what if you want those 4 links to go to 4 different switches, right? I mean, in that case, you know, it doesn't make sense to maintain the ordering.
Exactly. And perhaps for the benefit of the group, since this is time synchronization group, what maybe you can, if you can provide more elaboration on how you do 1588, we support the 1588 for TDMA, maybe more explanation.
Right. Okay. Yeah. So the TDMA, or sorry, the IEEE 1588 support for Corundum is basically as simple as possible in terms of what you can get on a NIC. So we have a hardware clock with, I think, 32 bits of fractional nanosecond resolution, so you can very precisely adjust the frequency that's running at from the host.
1 picoseconds, yeah.
Right. Yeah, I don't know what that number is off the top of my head, but I was thinking about, okay, if we're going to be updating this once a second and we want to be, you know, within a nanosecond, you know, how many bits do you need? It's like, okay, it's around 32 or so, so that works. And the core clock we're running this thing in is a 250 megahertz clock. So I will say there's probably some improvements we could make to the time synchronization. So one thing that I should just throw out here about Corundum is that I didn't know if this was even going to be possible when I started working on it. I didn't know if I was going to run into some, you know, major roadblock. So my idea is, okay, we're going to build this kind of as simple as possible and spend as little time optimizing as possible until we get something working, and then we'll go back and clean it up. So some of the PTP support is a little bit rough because we had to get it working for some of the experiments that we wanted to do, but now we can go back and kind of clean it up and improve things a little bit. So the hardware clock, I mean, I don't think there's much to do there, but it is running, the clock domain it's running in is the PCI Express clock domain. And the reason we did that is so we can have, you know, direct register access to that clock. But that's not necessarily the best solution. It might make sense to run that in a different clock domain that's going to be more stable than whatever the host is providing. So, I mean, I think that'll affect probably the holdover time and, you know, who knows what else. But for our applications, we're trying to do microsecond precision TDMA. So as long as we can time sync within a microsecond, we're good. We don't need to do any better than that. For other applications, you would need to do better than that. So yeah, we have the PTP clock, and then we take that and we synchronize it into all of the transmit and receive clock domains for all of the Ethernet MACs, and then those MACs will timestamp all of the incoming and outgoing packets, and then those timestamps are passed back to the data path and included in the completion data that gets handed off to the operating system. So we have a PTP clock, and then we provide hardware timestamps for every single transmitted and received packet. And I think we're providing those with a 1 nanosecond resolution. I think we threw out the fractional nanosecond field just to save space in the completions. So yeah. I think this is pretty standard to what I think a lot of NICs provide. I was looking at like the Mellanox driver to see what they're doing. A lot of NICs, they actually don't have a hardware clock on the NIC that you can adjust. They just have a free running counter, and then they map that onto PTP time with the software mapping, and then they run the same mapping on all the timestamps that are reported. So since we need the PTP time on the NIC to feed into the TDMA components, then we actually have to have the PTP clock on the NIC.
Just a comment. There are other applications today as well.
Yeah, you mentioned, you talked about a scheduler. You described your scheduler, but it wasn't clear to me how your scheduler will alleviate the incast problem, that incast congestion induced problem. You know, incast can cause congestion, and I'm not sure how your scheduler can solve this issue.
Incast.
This is it for me.
Oh, inside the network? I mean, so this is where inside some of the routing protocols that that we're going to be looking at for implementation on top of Corundum come into play. So one thing to keep in mind about circuit switches is that you basically don't have congestion inside of a circuit switch network, right? Because you have dedicated links from one end to the other. It's not like you're going through a whole stack of packet switches where you have lots of opportunities for congestion. You have just a dedicated link, whatever packets go in on one end or what comes out on the other end. So from that standpoint, congestion is a bit less of a problem as it would be for other systems. but this is actually one thing that we're looking at, because for some of the networks that we want to build, we will actually have packet switches at both ends, right? So you'll have hosts hooked up to a packet switch, and then you'll have an optical network that connects to another packet switch to another host. So you basically have two opportunities for incast and congestion, and we have some protocols that we're working on to try and work on that. And that's a little bit out of scope for what we're doing with Corundum specifically. We have a paper RotorNet and another paper Opera that discuss some of these protocols in more detail. And at some point, I'm going to be looking at implementing some version of that on top of Corundum, but it's not yet implemented.
Just one comment, Alex. In a few of our previous sessions, we have discussed the implementation of timestamping in NICs and means to measure. Yeah, it means to measure, and I think that there are existing approaches with existing NICs that are somewhat communal to what you presented. And it would be great to see how we can collaborate and standardize them or development them in tandem.
Sure.
So one question, Alex, when it comes to, like, let's say the implementation right now, like there are a lot of things, like for example the AXI or something there, like as like was mentioned, I think it was mentioned also by was brought up by Hisham. They're like more specific to, let's say, the Xilinx stuff. So let's say not necessarily, let's say, going for other FPGAs or something. Let's say if you want to move, let's say you have the option to move toward an ASIC, like how far you see like the design of Corundum is.
Oh, what do you mean? Like in terms of maturity, like?
Yeah, maturity, or like, let's say, are there roadblocks, or is that like architecturally like considered to do that, or?
Well, so from my point of view, the whole point of Corundum is the fact that you can go in and you can make modifications to it. And as soon as you spin an ASIC, then you lose that capability because you have a fixed function thing. But that doesn't. It just means that for the type of stuff we're doing at UCSD, it's just not something that we're interested in. But you could certainly do that if you wanted to, say, just use Corundum as a host interface and build some crazy packet processing SmartNIC kind of solution, and just use Corundum as the host interface for that, and then spin an ASIC. That's certainly something that's doable. To be honest, I haven't really thought too much about what kind of changes would be required to the HDL to make that possible. I know I'm probably designing more for FPGAs, so I'm using a lot of distributed RAM and whatnot, which is maybe not the best solution if you wanted to go for an ASIC implementation. But I mean, if somebody was serious about that, then there's probably some, that some of that could be, revisited.
I think we discussed, you and I, like about like a hybrid where you have a board that, let's say, has an FPGA, but the board hosts like things that if they go on a hardware, it's much better. I think I'm really trying to find like what would be like the big advantages. Let's say, remember, like when we're talking about, let's say, the clock itself, starting from there, or like RAM, or like a lot of things that I kind of think like they're getting compromised with whatever is off the shelf, let's say, for this dev boards.
Right. Well, I mean, you mentioned boards. I mean, this is something that we're not interested in at UCSD because we want to just be able to buy off-the-shelf hardware and use it. We don't want to be spending a huge amount of time spinning our own boards. But if somebody wanted to make a board that was optimized for Corundum, with timing in mind, then you could certainly do that. Well, so I will mention that with Corundum, we try to use as few board level resources as possible so that we're as portable between boards as possible. And part of that actually came from the first board that we were running on didn't even have DRAM. So we couldn't use DRAM even if we wanted to. But now that means that whatever board you want to run it on, doesn't matter if it has DRAM or not, and then whatever DRAM it has is available to whatever application you want to run on top. So that it was a little bit annoying in the first place. It's like, well, we're just gonna have to buffer all this stuff with the onboard, resources. But this now is kind of turned into an advantage because we're more portable, and that opens up basically whatever's available on the board to your applications. So if you wanted to do something more timing specific, we could certainly think about how to integrate that into the rest of Corundum in order to actually utilize those features. Now, for having built an FPGA-based NIC that supports PTP, I'm actually not super familiar with all of the design aspects that you need in order to do that properly. So I would definitely be open to having some discussions and fleshing that out, especially if this is something that people are interested in, making a board that's specific to running Corundum. The flip side is I know that there are a lot of existing NICs that kind of do similar stuff. Like I know Exablaze made some cards with timing in mind, and they're now owned by Cisco. So it's possible that one of those could perhaps be a slightly better fit than making something custom. But I don't know.
Yeah. Okay, I think we're on top of the hour. Any last question?
So I have a question. 802.1 QBV defines a time-aware shaper or scheduler. How does the Corundum scheduler compare to 802.1 QBV?
I need to take a look at that actually. Right now, I will say that the schedulers in Corundum are very, very simple. It would, because we've been trying to get the rest of the data path and whatnot operational. But for some of these more standard technologies, it would be definitely something that we'd like to look at to see if we can map what we have onto that. I would need to take a look at that standard to see exactly what its what the capabilities are.
Thank you.
Okay, I think that will be the end of today's session. So thank you for everyone for sticking around, and we'll have basically the video on YouTube available for whoever was not able to attend. And should we spoil it, what we're gonna have in 2 weeks? We'll keep it secret. Yeah, I mean, just a little hint. So the title is Clock Statistics, and I think a lot of you guys will enjoy. Awesome. Okay, see you everyone. Bye.
See you. Bye-bye.
So yeah,
Thank you.
Thank you, Alex.
Thank you, Alex.
thanks for the opportunity.
Thank you. Bye.